Imagine sprinting to catch a bus, lifting a grocery bag, or simply tapping your fingers on a keyboard. Every movement you make, no matter how small, relies on a silent surge of sodium ions inside your body, orchestrating the contraction of muscles and firing of nerves. But how can something as reactive and explosive as sodium be so essential to life? What makes this soft, silvery metal tick, chemically and physically? If it's never found in nature on its own, where do we get it? And how do we produce and control it safely? And beyond our bodies, what role does sodium play in technology and industries that shape our world? Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe and hit the notification bell so you will never have to miss another episode. Welcome to the new year, and as of today we will provide a new poll for the next week so you can choose what element we will discuss 2 weeks from now. For next week we will do another experimental deep dive for an element you did not ask for. And that element will be iron. Now, sodium at first glance doesn't look like the kind of metal you'd expect to be explosive. When freshly cut, it reveals a striking silvery white surface that gleams almost like polished aluminum. It doesn't stay that way for long. Within seconds, the bright sheen dulls as it reacts with air, forming a thin gray or white oxide layer. And that is also what we can see in this cube. Now, if you were to watch a block of sodium in open air, you'd see its surface slowly crust over, like fruit left out too long. It's soft and unassuming, almost like a piece of chalk with a metallic glow when fresh. Now, if we could take this sodium out of the cube and we could touch it with our hands in a perfectly dry, controlled environment, and this is something only professionals ever attempt, it would feel strangely soft and malleable. Unlike hard metals like steel or copper, sodium yields easily under pressure. Pressing on it would feel like pushing into firm clay or slightly dry toothpaste. It gives, but not instantly. At room temperature, it's cool to the touch, but not cold, and it has a very slight greasiness if stored in oil. However, any hint of moisture, say from sweat on your skin, could set off a reaction. Now that brings us to the most important question in life. Can you lick it? Well, you probably guessed it, but because sodium reacts instantly with water, including the moisture on skin, touching it with bare hands could result in localized burn. But licking it, that would be much worse. Your tongue is covered in saliva, exactly what sodium needs to start the reaction. Now picture this. As soon as the metal hits the wet surface of your tongue, it would sizzle violently, producing hydrogen gas and forming sodium hydroxide, a caustic substance that can burn through flesh. In a fraction of a second, you'd experience a sharp chemical burn and possibly an explosive pop from the gas being released. It's the kind of reaction that could cause serious injury into your mouth and your throat. In short, sodium may look harmless, soft, pale, almost inviting, but it's not something to be taken lightly. It's a metal with an unpredictable streak, one that reacts with the very things we take for granted. Air, water, even the dampness of a curious tongue. So, while it may not look dangerous at first, sodium is best observed from a safe distance or through a lab window, not a taste test. Sodium has been in use by humans long before we understood it was an element. Ancient people didn't know about sodium metal, but they certainly knew about its compounds. Salt, which is sodium chloride, has been prized for thousands of years as a seasoning and a preservative. In fact, salt was so valuable in antiquity that Rome's soldiers received salarium, a salt allowance, as part of their pay. This is actually the origin of the word salary, meaning you were literally worth your salt. Another important sodium compound of ancient times was natron, a natural blend of sodium carbonate salts. The ancient Egyptians used natron to mummify bodies and for cleaning. It was a critical mineral in their culture. The name sodium itself has interesting roots. In medieval Europe, a common remedy for headaches was a type of sodium compound, sodium carbonate or soda ash. The Latin name for this remedy was sodanum, which likely came from Arabic suda, meaning headache. So the term sodium traces back to those old headache cures made from soda. The chemical symbol Na comes from a different source, the New Latin name natrium, referring to the Egyptian natron. In other words, Na is a nod to natron, the soda salt that Egyptians used extensively. Despite humanity's long familiarity with salt and soda, the elemental metal sodium was not isolated until 1807. The English chemist Sir Humphrey Davy, we talked about him many times before, discovered sodium when he applied a newly invented electric battery to molten sodium hydroxide, caustic soda. Using electrolysis, Davy succeeded in freeing sodium metal for the first time. He described seeing small globules of a shiny new metal appear, pure sodium. This was a major achievement in chemistry at the time. Davy also isolated potassium using similar methods shortly before. Initially, some scientists proposed alternative names, for example natronium, but in the end Davy's name sodium stuck, and later chemists like Jöns Berzelius adopted the symbol Na to honor the natrium-natron connection. From that point, sodium metal became a subject of study and eventually an industrial product. By the late 19th century, methods were developed to produce sodium in larger quantities. Interestingly, one early driver of sodium production was the manufacture of aluminum. An old process for refining aluminum metal required sodium, so demand for sodium spiked in the 1800s. Now, this is the cue for everybody that wants to nail me to the cross again for using the word aluminum instead of aluminium. But soon after, new aluminum processes reduced that need. In the 20th century, other uses for sodium metal and its compounds took over, and the production methods improved greatly, as we will discuss in a moment. Sodium is a chemical element with atomic number 11, which means each sodium atom has 11 protons. It lies in group 1 of the periodic table among the alkali metals. And like its alkali metal buddies, lithium, potassium, etc., sodium has just one valence electron in its outer shell, and this accounts for much of its behavior. In terms of appearance and texture, pure sodium is a silvery white metal, like we've seen in the cube, with a soft, almost waxy consistency. In fact, sodium is so soft that you can cut it with a knife. A fresh cut through a sodium metal ingot will reveal a bright, shiny surface. However, you rarely get to see that shine for long. Sodium tarnishes almost immediately when exposed to air. It reacts with oxygen in air, forming a dull white coating of sodium oxide, and further reacting to sodium hydroxide with moisture. And we've discussed it earlier in the Can You Lick It segment. For this reason, sodium metal is usually stored under oil or in an inert atmosphere to keep air and water away. Several physical characteristics set sodium apart from familiar metals like iron or copper. For one, sodium is extremely light. Its density is about 0.97 grams per cubic centimeters, which is lower than water's density. This means solid sodium will actually float on water, at least for the few seconds before it will react violently. Sodium also has a low melting point for a metal, about 97.8 degrees Celsius or 208 degrees Fahrenheit. That's just hot enough to melt in boiling water. Its boiling point is 883 degrees Celsius or 1621 degrees Fahrenheit. Sodium is a good conductor of electricity and heat, as you'd expect for a metal, though one rarely uses it for wiring due to its reactivity. The element has only a single stable isotope in nature, sodium-23. Any other isotopes of sodium are radioactive with short half-lives. Now, chemically, sodium is famous for being highly reactive. It readily undergoes reactions with many other elements and compounds, often releasing a lot of energy. The root cause is that lone valence electron. Sodium atoms want to lose that electron to achieve a stable configuration, and in doing so, they form sodium ions and generate heat. One of the hallmark reactions of sodium is with water, which we've discussed before. If a piece of sodium metal is dropped into water, stand back. Sodium will immediately start to react, producing sodium hydroxide and hydrogen gas. This reaction is extremely exothermic, heat releasing. The hydrogen gas may ignite from the heat, and often sodium will skitter around the surface of the water as it rapidly decomposes. With larger pieces, the hydrogen can catch fire or even explode, yielding a characteristic orange flame. It's a spectacular demonstration of sodium's reactivity, and also a reminder of why pure sodium must be handled so carefully. Even exposure to air is enough to trigger sodium's reactivity. As mentioned, sodium metal will react with oxygen from air to form sodium oxide on its surface. If heated in air, sodium burns with a brilliant yellow flame. That yellow color is a signature of sodium's presence. It comes from excited sodium atoms emitting light, the same effect that gives street sodium vapor lamps their glow. In fact, burning sodium in excess oxygen can form sodium peroxide, a higher oxide. Firefighters have to be cautious with sodium fires because using water will just increase the flames due to the water-sodium reaction. Special dry extinguishing agents are needed. Sodium readily combines with non-metals. It reacts vigorously with halogens like chlorine, bromine, etc. to form sodium halide salts. For example, the reaction of sodium and chlorine gas produces sodium chloride, table salt. These reactions can be violent as well, given sodium's eagerness to hand over its electron. With acids, sodium metal reacts to produce hydrogen gas, similar to the water reaction, since most acids supply water or hydrogen ions. In all its common compounds, sodium exists as the sodium plus cation, a positively charged ion. It has an oxidation state of +1 in basically every sodium compound, since it loses one electron. Sodium ions in solution are quite stable and generally colorless. They don't impart color to ionic solutions, unlike some metals such as copper. The sodium ion is non-toxic in moderate amounts. Indeed, it's a normal part of our body chemistry, though certain sodium compounds can be hazardous due to the other part of the compound. For instance, sodium cyanide is extremely toxic because of the cyanide, not because of the sodium itself. Even though we don't find lumps of sodium metal lying around, sodium is actually abundant on Earth. It's the sixth most abundant element in the Earth's crust, making up about 2.6% of the crust by weight. Sodium is widespread because it forms many common minerals and salts. However, due to its reactivity, all the sodium in the environment is bound up in compounds. One of the most familiar sodium compounds is, of course, sodium chloride. Huge deposits of sodium chloride exist around the world in the form of rock salt, the mineral called halite. These deposits often come from ancient oceans that evaporated, leaving thick layers of salt behind in the soil or buried under rocks. For example, large underground salt mines are found in places like the United States, United Kingdom, India, China, and many other countries. All remnants of dried up seas from millions of years ago. Humans have harvested these salt deposits for ages, as salt was crucial for food preservation and seasoning. In addition to solid deposits, an immense amount of sodium is dissolved in oceans. Seawater is salt primarily because of dissolved sodium chloride. On average, seawater is about 3.5% salt by weight, and sodium is about 1.1% of the weight of the seawater. To put it in another way, a liter of seawater contains approximately 30 grams of sodium chloride. That's a lot of salt spread through the world's oceans, which serves as a practically inexhaustible source of sodium in compound form. I must say, 30 grams seems a little bit low, because seawater is extremely salt when you taste it. Aside from sodium chloride, many other minerals contain sodium. Silicate minerals in the Earth's rocks, like certain types of feldspar and clay, have sodium as part of their structure. For instance, common feldspar minerals in granite contain sodium, aluminum, silicon, and oxygen. These minerals are very stable, not soluble in water, so they lock sodium away in rocks. There are also sodium-bearing minerals like soda ash, sodium carbonate, which can be found in dry lake beds and playas. The previously mentioned natron is one example historically obtained from dry lake shores in Egypt. Another notable mineral is cryolite, sodium aluminum fluoride, which was once mined in Greenland and used in aluminum processing. Interestingly, sodium is also present beyond Earth. In the sun and stars, sodium can be detected by the bright yellow spectral lines it produces. Early astronomers in the 19th century, like Fraunhofer, identified sodium in the sun's light by these lines. Sodium atoms are even found in places like the thin atmosphere of the moon and some comets. So sodium is a common element in the universe, though not among the very most common. Isolating sodium metal is a little bit tricky because of its tendency to react. You can't get sodium out of compounds by simply heating or chemical reducing it with carbon. Carbon will reduce some sodium compounds, but the sodium metal produced tends to vaporize or react again. The breakthrough in obtaining sodium was achieved by electrolysis, using electrical current to split a sodium compound. As mentioned in the history section, Sir Humphrey Davy first got sodium by electrolyzing molten sodium hydroxide in 1807. However, sodium hydroxide melts at a high temperature, and that method isn't very efficient on a large scale. In the late 1800s, there were a couple of improvements. One was the Deville process, which involved chemically reducing sodium carbonate with carbon at about 1100 degrees Celsius. This did produce sodium metal and was used commercially in the 1860s, primarily to supply sodium for making aluminum. Shortly after, another approach, the Kastner process, was developed, which electrolyzed molten sodium hydroxide to yield sodium. Modern sodium production, however, uses a more effective method known as the Downs process. The Downs cell, named after its inventor, was introduced in the 1920s and is still the basis for sodium manufacturing today. In the Downs process, molten sodium chloride, basically a liquefied table salt, is electrolyzed. Now, pure salt alone has a very high melting point, 800 degrees Celsius, so in the Downs cell, the salt is mixed with a little calcium chloride. Adding calcium chloride lowers the melting point of the mixture to about 600 degrees Celsius, which saves energy. The molten salt mixture is contained in a cell with a positive anode and a negative cathode. When an electric current passes through, the salt breaks down. Chlorine gas is released at the anode, chlorine is a byproduct, and liquid sodium metal is deposited at the cathode. Sodium, being less dense than the electrolyte mixture, floats to the top and can be drawn off. The key reaction in the Downs cell is this. Because calcium is present but calcium ions are less easily reduced than sodium ions, only sodium is deposited. The calcium mostly stays in the melt and the process can continuously produce sodium as long as you add more salt and remove the products. Using the Downs process, industry produces on the order of hundreds of thousands of tons of sodium metal per year. It's actually not a huge volume metal compared to iron or aluminum production, but it's significant nonetheless. The metallic sodium is usually cast into ingots or stored under oil and shipped in airtight containers to prevent any contact with moisture. Even a small amount of water during storage or transport could be dangerous, so handling and packaging are critical. Now, sodium's uses fall into two broad categories: uses of sodium compounds, which are numerous and huge in scale, and uses of sodium metal itself, which are more specialized. We will cover both. Now let's start with the compounds. You encounter sodium compounds every day. By far the most prevalent is sodium chloride, or common salt. Salt is used worldwide as a food seasoning and a preservative. It has been a cornerstone of human civilization, think of the word celery, as we noted. Even today, massive quantities of sodium chloride are used, not just in food, but also for de-icing roads in the winter. Spreading salt on icy roads helps to melt the ice by lowering the freezing temperature of water, making driving safer in cold climates. Another indispensable sodium compound is sodium bicarbonate, known as baking soda. In the kitchen, baking soda releases carbon dioxide gas, which it reacts, for example, with acidic ingredients, which makes baked goods rise and turn fluffy. Baking soda is also a mild anti-acid. It can relieve heartburn by neutralizing stomach acid. You'll find it used in cleaning products and even in some fire extinguishers. When heated, it releases carbon dioxide, which can smother flames. Sodium carbonate, washing soda or soda ash, is another major compound. It has strong cleaning and water softening properties. One of its big uses is in making glass. When you heat a mix of sodium carbonate, sand, silicon dioxide, and limestone, calcium carbonate, you get soda lime glass, the most common form of glass used in windows, bottles, etc. The sodium carbonate lowers the sand's melting point and helps the ingredients fuse into glass. Sodium hydroxide, caustic soda or lye, is a very strong base used extensively in industry or in our garage as a chemical. It's produced in huge amounts, often via the chlor-alkali electrolysis process, which actually makes chlorine gas and sodium hydroxide from salt water. Sodium hydroxide is vital for making soap. In traditional soap making, fats are saponified by lye to produce soap. If you want to know more about that, watch the movie Fight Club. It's also used to manufacture paper, to break down wood fibers, to produce detergents, to refine petroleum, and as a general purpose strong alkali in many chemical processes. If you've ever used drain cleaner or oven cleaner, the active ingredient was likely sodium hydroxide, which dissolves grease and organic matter. There are many other sodium compounds with important uses. Sodium nitrate and nitrite are used for curing meats and as fertilizer compounds. Sodium phosphate is used in cleaning agent and food processing. Monosodium glutamate is a flavor enhancer in the cuisine. Sodium benzonate is a food preservative. Sodium fluoride is added to toothpaste and water supplies to help prevent tooth decay. The list goes on. Sodium forms a dazzling array of salts, and collectively, sodium compounds are some of the most widely used chemicals in the world. In fact, in terms of volume, the biggest uses of sodium by mass are in the form of compounds like these, each with millions of tons produced annually. So what about the sodium metal itself? While most sodium ends up with compounds, the elemental metal does have some specialized applications. One notable use of liquid sodium metal is as a coolant in nuclear reactors. Certain type of advanced nuclear reactors, fast breeder reactors for example, use liquid sodium to transfer heat from the reactor core. Sodium has an excellent thermal conductivity. It carries away heat quickly and a very high boiling point, around 883 degrees Celsius like we've discussed, allowing it to remain liquid and carry heat at a high temperature without needing pressurization. In a sodium-cooled reactor, liquid sodium flows through the reactor core, picks up heat from the fission reactions, and then flows through a heat exchanger where it gives that heat to water, producing steam to drive turbines. The advantage is that the reactor can run at high power density and normal atmospheric pressure. The downside is, of course, that sodium is reactive. If it leaks and contacts water or air, fires occur. But with careful engineering and monitoring, and using sodium-potassium alloy in some cases to remain liquid at room temperature, sodium-cooled reactors have been successfully operated. This is a fairly exotic use, but it underscores sodium's unique properties. Few substances remain liquid at high temperature and don't absorb neutrons much. Sodium does those things well. Another use of metallic sodium is in the production of certain metals and chemicals. For instance, sodium is used to refine some reactive metals from their compounds. A classic example is the production of titanium metal. Titanium cannot be easily reduced by carbon. Carbothermic methods don't work well. So one method called the Hunter process uses sodium metal to reduce titanium tetrachloride into titanium metal and sodium chloride. Similarly, sodium has been used to reduce zirconium and other specialized metals, although newer methods or other reducing agents like magnesium have in some cases replaced sodium. It was very important in early metallurgy of those elements and is still used in certain processes. Sodium metal is also employed as a chemical reagent. It's a strong reducing agent. It readily donates electrons. In organic chemistry, for example, sodium is used in the Birch reduction, a reaction that can partially hydrogenate aromatic rings using sodium ammonia. Sodium metal is used to make reagents like sodium borohydrate, a powerful reducing agent used in pharmaceutical synthesis, and sodium hydride, a strong basis for organic reactions. Another well-known compound is sodium azide, which is made using sodium and is famous for its use in car airbags. When ignited, sodium azide rapidly decomposes to nitrogen gas, inflating the airbag in a fraction of a second. The sodium metal byproduct is then absorbed by other materials in the airbag system. In the realm of materials, sodium forms an interesting alloy with potassium, NaK. That is liquid at room temperature. This NaK alloy is sometimes used as an even lower melting point coolant or reagent. Sodium itself is solid at room temperature, but mix it with potassium and you get a liquid metal that still has much of sodium's excellent heat transferability and, unfortunately, its reactivity. NaK is extremely reactive and even more easily ignites in air, so it must be handled with great caution. Sodium is also a component in certain electrical technologies. High-pressure sodium vapor lamps and low-pressure ones were once common for street lighting. These lamps contain a bit of sodium metal that vaporizes when the lamp is on. An electric current passing through the vapor causes the sodium to emit a distinctive yellow-orange light. Sodium vapor lamps are very efficient in terms of lumens per watt and were widely used to light highways, parking lots, and streets with their monochromatic golden glow. These are gradually being replaced by LEDs now, but many sodium lamps are still in operation around the world. The brilliant yellow flame of sodium also find a niche use in astronomy. Powerful lasers tuned to the sodium D line, wavelength 589 nanometers, are used to create artificial guide stars to the upper atmosphere. By exciting sodium atoms in the thin layer of our atmosphere, left by meteors, these lasers produce a bright dot that telescopes can use as a reference to correct for atmospheric distortion, adaptive optics. It's a complex high-tech application, but interestingly, it relies on the same basic properties you see in a simple flame test in chemistry class. Historically, metallic sodium had other uses that have since declined. It was once used to make tetraethyl lead, the anti-knock additive in leaded gasoline, and in certain types of synthetic rubber production. Sodium was even used in early stages of making gasoline additives and other organometallic compounds. However, as technologies changed, for example, leaded gasoline was phased out, some of those uses diminished. Now, when we ask how does sodium help your muscles move, we're really exploring the role of sodium ions in physiology. Sodium is absolutely essential for the normal functioning of nerves and muscles in the human body and in the bodies of most animals. It might be surprising that a metal known for blowing up in water is a linchpin of biology, but in ionic form, sodium is perfectly suited to this job. The human body contains around 0.1 to 0.2% sodium by weight. In our blood and in our extracellular fluids, sodium is the primary electrolyte, positively charged ion, present. One of sodium's critical roles is to maintain the proper fluid balance and blood pressure. Sodium ions in the blood help ensure that water is distributed correctly inside and outside cells. This is often referred to as maintaining osmotic equilibrium. This is why having too little sodium, a condition called hyponatremia, can cause cells to swell with water. And too much sodium, hypernatremia, can dehydrate cells. Both states are dangerous, but beyond fluid balance, sodium is a key to something even more dramatic, generating electrical signals in nerve cells. Your nerves and muscles communicate via electricity. Not the kind of electricity that powers appliances, but tiny bioelectrical impulses. These impulses are called action potentials, and sodium is a star player in producing them. Now here's a simplified explanation. Every nerve cell, neuron, maintains a concentration gradient of sodium and potassium across its cell's membrane. Basically, it pumps sodium ions out of the cell and potassium ions into the cell. This is done by the sodium-potassium pump, a molecular machine that uses energy, ATP, to keep sodium high outside the cell and low inside, and potassium the opposite, high inside, low outside. Now, as a result, the outside of the cell has a positive charge relative to the inside, creating an electrical potential like a charged battery. Now, when a nerve cell needs to send a signal, special channels in the membrane open and sodium ions rush into the cell, following their gradient. Now, because sodium is positively charged, this influx makes the inside of the cell suddenly more positive. This change in voltage is the nerve impulse. Now, the depolarization caused by the sodium triggers a cascade of channel openings along the nerve's length, propagating the electrical signal rapidly down the neuron. It's like a wave of positivity moving along the wire of the nerve fiber. Now, when that nerve impulse reaches a muscle cell, it causes the muscle cell's membrane to also open sodium channels and let sodium flood in momentarily. That electrical spike inside the muscle cell triggers internal calcium release, which ultimately causes the muscle fiber to contract. In essence, sodium is the trigger for muscle contraction. It's the messenger that carries the "move now" command. Without sodium, our nerves could not fire and our muscles would not receive the signals to contract. Now, after the action potential passes, the sodium-potassium pump pushes the sodium back out and potassium back in, resetting the original balance and readying the cell for the next impulse. This cycle repeats every time a nerve fires or a muscle fiber contracts. Think about it. From the simple action like blinking your eye or lifting your arm to the most complex thoughts in your brain, sodium ions rushing through channels are making it happen. Now, besides nerve impulses and muscle contractions, sodium has other physiological roles. It helps nutrient absorption in the gut. Many nutrients are co-transported with sodium ions into cells, and it's involved in kidney function and regulating blood volume via hormones, like the renin-angiotensin-aldosterone system, which adjusts sodium reabsorption to control blood pressure. I really hate the biological pieces of these videos. Because sodium is so vital, our bodies enforce a tight balance. We need to consume a certain amount of sodium in our diet to replace what's lost in sweat and urine. However, we don't need huge amounts. The minimum physiological requirements for an adult is estimated to be only about 500 milligrams of sodium per day, which is roughly a quarter of a teaspoon of salt. Most people easily consume many times that amount. Salty foods are common and tasty. An excess of sodium over time can contribute to high blood pressure in some individuals, as well as other health issues. Thus, doctors often advise moderating salt intake. On the flip side, if someone loses too much sodium, say through heavy sweating and only drinking plain water, they can experience muscle cramps, weakness, and even confusion or seizures. That's the hyponatremia we mentioned. That's why sports drinks and rehydration solutions contain a bit of salt to replenish sodium along with water, ensuring muscles and nerves keep working properly. Sodium is a remarkable element that touches our lives in multiple ways. It's a chemical paradox. As a pure metal, it's so reactive that we must tame it in oil. Yet, as an ion in salt, it's so benign and common that our bodies rely on it. Next time you shake a salt shaker, see a streetlight glow amber, or feel your heartbeat, muscles flex, remember the humble sodium atoms at work. This element, so common and so reactive, truly bridges the gap between the mineral world and the living world, from rock salt in earth to the firing of neurons in our brain. Sodium's story is a shining example of how the elements of the periodic table underlie the ordinary and the extraordinary processes of life and civilization. Sodium keeps our chemistry lively and industries running and our muscles moving. So stay salty in moderation, of course, and appreciate the science that lets this little element have such a big impact on our world. Now, we would like to thank the members that support our channel. Thanks for doing that. We still really appreciate you. Now, if you think we missed anything, tell us in the comments. And if you want to know more about another reactive element, take a look at this video about calcium next.